Hey guys, so we're continuing our discussion of energy with today the subtopic of work. So remember, the framework we're in here is we're talking about energy, and energy is something that a system has. It possesses energy. Then there are two ways that energy can transfer, like entering or exiting a system, switching between systems, and those processes of transferring energy back and forth are called heat and work. And we talked about how those are the only two ways that energy can transfer. The key point there that I'm going to reiterate once again is that heat and work are not something that an object has. They're something that can be done to an object. It's a word describing the process, not the actual physical thing. So we've talked about heat, and I want to refresh your memory how we define heat, because we said that heat is any energy transfer that's driven by a temperature difference. And we went through and drew the picture of all the little molecules, talked about the different ways that temperature difference can drive heat energy, radiation, conduction, and convection. Work is defined in a little bit of a roundabout way. So first let me write the definition, and then you'll see what I mean. Okay. Work is any energy transfer that is not driven by a temperature difference. So in essence, what we're saying is it's all the rest, right? You look at the world and you see all these different ways energy can transfer. Some of them are heat, and then everything else is work. That's how it's actually defined. It's any energy transfer that isn't heat is work. So, with that being said, you can imagine that work is quite a large subject. And so there are many, many different types of work, and they all depend on what scenario you're involved with. And so what we're going to do is we're going to look at some of the different scenarios in which we may be able to derive a formula for work. Before we do so, let's talk about the units. Remember that the units of energy were joules. And that's denoted with a J. And so, when energy is being transferred, we're still measuring amounts of energy that are transferred, and we're still measuring them in joules. So that goes for the units of heat and the units of work as well. Those are all equal to joules. So, and then remember that a joule in base SI units is kilograms times meters squared times seconds squared. So joules is really just a nickname for these units. Okay? So what are some possible scenarios that work could come up in, like we said? Well, the first thing is we have electrical work. So I'm going to write that as W subscript E. Now because that's a subscript there. I'm not writing the word we. Because of the fact that this is a thermodynamics class, which is sort of on the opposite side of physics from an electrodynamics class or electrostatics, or where we would really study this type of thing, I'm not going to go through the derivation of this. Okay, you've had this in tech physics and you've had it explained in more detail. I'm just going to write down what the answer was. So electrical work was determined by taking the voltage and multiplying it by the charge. Okay? You just multiplied those two things. So however much charge and however much electromagnetic potential, or voltage as we call it, was pushing that charge. And that was the work that was done. Okay? There is another type of work, which is mechanical work. Actually, I'm going to write this over here because I want to leave this open. So this subscript M is for mechanical. And you may remember from tech physics that the definition of that was a force times a distance. Okay? And this is sort of the head honcho of a lot of other types of work underneath of it. So it's a big category heading. So some examples that our book gives of work done by moving a force through a distance are springs, spring work, shaft work, like any sort of spinning turbine shaft or anything with a torque on it produces work. Any kind of piston, because it's got a force and it's moving through a distance. Anything that is mechanical, really, that is producing work. We're going to always boil it down to this basic formula. All right? And so far, this is all still just a review. So for this class, I want to quickly move into what our thermodynamic work is going to look like. And it comes from this. So what let's do is let's look at a specific system. I have a gas that is in a chamber here, and above it there's a piston, all right? So this is my gas. Now, as you can imagine, if this gas were to expand, and for this study right here, we're only thinking about the work, and so we're not caring what makes it expand. Sure, maybe it's being heated to expand, maybe something else. We're just saying, okay, take it as a given, this gas is expanding. We know that when it expands, it's gonna push this piston up. So it's doing work. This actual gas itself is doing work. And that's what we're gonna derive the formula for, because that's the main thing that we care about for today. So when this piston is pushed by this gas, it moves through a specific distance. So let me be a little more exact and call this delta x for the change of position, right? Force times a delta x, that's the fancy way of saying distance. And let's call this, right here, this distance x1 that the piston starts at. And then let's say that the gas expands and it pushes the piston all the way up to here. So that's the new position of the piston, and then all this filled with gas. Well, this distance all the way up to here is going to be x2. And so delta x, this distance in between, is of course x2 minus x1. That's what the delta of anything means. It's the difference between the final and the initial states. All right, so the last thing we need to add to our diagram is some information about the piston. We're going to say that the piston is being pushed up with a specific force on it, and we can just call that F. It's some unknown force, but we know that it's there. And then this piston actually has an area, and the way I've drawn this, we're looking from the side, but you can imagine what I mean. I mean the flat part of the piston that's pushing into this volume of liquid. So right along here, I'm going to mark that as A for some area. So let's go over here to our formula that work is force times distance. Actually, I'll leave that one because I don't want to mess with it. I'll write this over here. So we have work equals force times delta x, which we know is force times x2 minus x1. Now, I would like to put this in terms of something that I know about the system, right? How do I get the force of a system? We really haven't discussed anything about how to measure the force coming off of a liquid or a gas or whatever's here. But what we have talked about is the pressure, okay? We're pretty comfortable with dealing with how to calculate the pressure of that gas or anything else involving the pressure. So what I can do, take a second to think about this if you need, is I can write this as the pressure times the area instead of the force. Now this area is of course the area of that piston, because think about what pressure is. If there's a pressure on that, we've defined pressure to be force over area. Okay, we've done lots of practice problems with that. And so I can rearrange that and say that force is pressure times area. And I'm doing this substitution so that I can eliminate that force, which I don't really care about, but I care about finding out how the pressure affects things. Now watch this, 2 more lines. if I were to distribute this area, distribute it across this, what would I get? Notice that the area of this tank is the size of the piston, whatever the base of that piston is, times this height. That's going to be the volume, right? So I take that piston area, multiply it by the height, and I have my 3 dimensions to find me the volume of that container. So if I multiply this area by this height, x2, what I get is volume 2. So I'm going to write this. And then I multiply the area by x1, the initial height, and I get volume 1. Hope you can see that. By multiplying an area with a depth or a height is going to give me a volume. And these are the volumes of those gases, final and initial state. And so finally, I'd like to tidy up my result by using the delta notation and just calling this delta V. Okay? So notice that work from an expanding fluid or work going into a shrinking fluid, whatever the fluid's doing, we can deduce that work by using P delta V. So that is an important formula. Okay? All right, moving on, we have a concept of power. Now, power is, the way I think of it is just ask it by a question, right? We know that work is a transfer of energy, so power is asking, how fast can that energy transfer? And so the way we define it is we take the work and we divide it by the time. Now, don't get confused with temperature, okay? This is a scripty lowercase t. I hope that it's obvious that it's set apart from my big uppercase T for temperature. This means delta T, or what time interval did this happen in. So what I'm literally calculating here is how much energy got transferred, that's work, and divide it by how much time did it take to transfer that energy, right? I'm answering this question, how fast can the energy transfer? And this is power. Now, in some classes we use P for power. In this class, P is taken for pressure. Capital P we've already used. So what we do is we use W dot, which is a notation that you've seen before. We had Q dot, which is heat per unit time as well, okay? So this dot over it means that we're going to be dividing it by the time. Okay, so you're going to have to get used to this. It can take a little bit to get used to. When you see a straight up W with no dot, it means work. When you see a W with a dot over top, that means power, and it's the work with the time in the bottom, all right? So it becomes really, really relevant to real-world applications because it turns out that in a lot of cases, we don't care how much energy got transferred. We care about how fast it happened. Consider a sports car that gets up to a certain energy, right? And by that, we usually are concerned with speed. But remember, kinetic energy is 1/2 mv squared. So the speed indicates the energy. So if I want it to get up to 1,000 kilojoules of energy, then, or 1 megajoule. So if I want to get up to 1 megajoule of energy, does it make a difference whether or not from 0 I can go to 1 megajoule in 2 seconds or in 2 minutes? Well, it's the same amount of energy, but what we care about is how fast can it get that amount of energy? How fast can we pump that amount of energy into that sports car? And that is power. How? We have to not only care about the 1 megajoule of energy that we put in, but we also have to care about how much time did it take. And so as you can imagine, the sports car example, horsepower turn out to be the imperial units for power, okay? And here is the units for metric. We have a joule, which is energy, and we divide it by a second. And this is a watt. Okay. Joules per seconds are watts, and then in imperial, we have horsepower. Okay, so a watt is the SI unit of power. Now, I want to go back over here where I left blank space and make a quick note about electrical energy, because in practice problems this may come up, so I want to review this. Just like over here we got power by dividing by time, I want to take this whole equation and divide it by time. So actually I'm going to write it on a new line. So electrical work over time equals the voltage V times the charge divided by the time. So this is that equation. I've just taken it, divided by the time, and of course we've just discussed how this comes out to be power. Remember, W dot is the symbol for power. And we have our voltage there, and then charge per unit time, well, that's current. And so you remember that the SI unit for current is the amp, and the symbol for it is I. So this is a very familiar formula, and it says that electrical power equals voltage times current. It might also be familiar to you if I write out the units that this is in. Lift the board a little bit. Power is, as we say, measured in watts. Voltage is measured in volts. And then, like we just said, we have current in amps. So watts equal volts times amps. That's not an equation about work so much as it's an equation about power, because watts are power. So this is an electrical power equation. And again, it's like saying how much electrical energy do we have, but also how fast was it transferred. I don't care how much energy I get if it takes way too long. I want my energy in a specific amount of time, right? I want it now. I want it in my window of time. A quick mnemonic that you may have seen for this is drawing a triangle and putting, let's see, watts up top with a bar over it to indicate division. And then down here we put volts. And then down here we put amps. And this is like a little bit of a childish way to do calculations, but it works. If you want to calculate one of these three things, you cover up the one that you're interested in and see what's left. So for instance, if I want to know the watts, I cover up watts and I say, look, what's left is volts times amps. So I get my watts. If I want to know, let's say, amps, I cover it up and I say, look, it's watts divided by volts. So then I get my amps. So whatever you want to cover up. Okay? All right, new board. There's an interesting note that I want to make about the distinction between what energy a system has and what work or heat is being experienced by the system, the transfer of that energy. And so I'm going to draw a phase diagram here. And it doesn't matter which two properties you have. You could even imagine it 3D if you want to picture the PVT surface. But the point is that we've been dealing with points on this phase diagram. And these points have coordinates, and I know this is only 2D, but I'll label it with all three coordinates. P, T, V, right? These are properties. So this is a state property. So let me write that. And the key point that I'm trying to distinguish here is that this depends on the state. So the key word is state. I'm going to say something really, really obvious, but it's actually fairly philosophical as well. A mathematical point does not know how you got to it. So what I mean is that we've talked about process paths, and we could have gotten to this state from any other state. We could have had a state here, and we came this way. Or we could have had a state here, and we came up to it. Or maybe over here and we came down to it. These are possibilities for where we used to be, or what our old state was before we got to this one. And what we're saying is, with this state property, this point in itself carries no information about where we used to be or how we got where we are. There's no way that it can know. All it is a collection of variables. Remember, that's the definition of a state. It's a collection of the properties that we care about. So it's just numbers. The pressure is this, the volume is this, the temperature is this. Can't say anything about where we came from. So that's what these points represent on a phase diagram. Work and heat are what we call process paths. Sorry, I'm getting ahead of myself. These are called path functions, and then the definition of path functions mean that their value depends on the process paths, okay? So, on our diagram, let me show you what this means. If I go from this state to this state, like that, along this process, that's going to be a different amount of work and heat than if I were to go along this process. Because work and heat care about the distance that we traveled or the path that we took. They're not like these things, pressure, temperature, and volume, that just care about where we're currently sitting. They remember where they've been. They depend on where they've been. So literally, just as an example, maybe one of these paths I get 5 joules, and the other one I get 8 joules. The actual answer I get depends on which path I take from point A to point B. The reason why we're touching on this, it may seem a little bit that I'm running on about this, it's because this is a really kind of fundamental point, but it actually involves a lot of calculus. And so I'm trying to skim over that for the purpose of this class and just say the important thing you need to take away is that work and energy depend on the path. They are path functions. All right, so I think that that's all I have for today, okay? And the next time, next lecture, I want to talk a little bit about putting this all together and deriving the first law of thermodynamics.